streaming and anomaly detection platform single-handedly. Anuj, over to you.
First of all, thank you for great introduction. Yeah. Good afternoon, everyone. So today I am going to talk about a very interesting problem that we saw, like how to handle real-time analytics with the mutable data. So if you think about, we usually think of analytics is good for solving queries at a high scale. But if you think from the fintech perspective, scale is not the only problem. Hard part for us is the mutability of the data. So that is the more mutability of data is the hard problem for us other than scale. So most analytical systems are good if you think about if data is append only. Then we just store the events, we aggregate them, and then we serve from the storage layer. And that is the happiest path for us. But fintech data does not work that way. So one payment entity goes multiple mutation again and again. And that's make the problem hard, because when you think about that, then if your architecture is not designed that way to handle the mutability, then you have to choose between correctness and speed. And that's become a very interesting architectural trade-off, that how you serve the analytical query fast enough, even with the correctness, keeping the correctness as cheap for the mutable data. And that is the topic I am going to talk about today over the next 20-25 minutes, that how we solve this mutability problem, why mutable data is hard, and what we work out, what's not work out for us, and what are the architectural trade-off and journey that we have done. So let's move on to the next slide. In terms of objective, our objective was very simple. We initially want to build a real-time system and for the payment data. And our most of the use cases are OLAPs. So like use cases that we want to serve as like merchant dashboard analytics, some use cases like anomaly detections, success rate monitoring. So most of the use cases are OLAP based. And at the same time, we want a sub-second latency performance also. And that's another thing. Also, we want to, so if you think about this, then we not only covering the analytical system that is fast enough, we also need an analytical system that is fresh and able to serve the mutable data. Whenever data is changing, it's able to handle those also. So before we deep dive on the architecture or our journey, let's first understand about the data nature itself, like how the data in fintech changes. So if you think about a payment entity, it's not an static record that it comes in and you write it once. It's more like a mutable entity. And if you think about payment, it go through multiple life cycle, and in its life cycle, it go to the multiple state transitions. So for an example, if you take a payment is first go to the created state, then it's moved to the authorized, then it go to the settled, then it go to the captured. So it's go to the many more updates after that also. So in its whole life cycle, a payment can go to the 10 to 15 transitions states. So that is the highly mutable state change that is happening inside a payment entity. And we are not dealing with that we talk about, like not a single entity that written once and you are happy with that. We have to keep changing that data again and again. If I talk more about real-time example for this, so take an example like a payment created at 10 o'clock in the morning, and within a few seconds, if you can see that it's had changed its state 4 times, and it's not stop here. Even these updates goes beyond few hours also, and even we have to handle the updates that come even days after also. Like in the case of settlement, in the case of refund, there will be updates that can goes beyond the days also. So the system that we are building, it has to handle the 2 things. First thing, it has to handle the rapid transaction, that payment is changing rapidly within a few seconds, and it also has to handle the later state changes, like when the updates are coming few days later, it has to handle that also. And how it's affecting like your both type of workload. So if your state is getting updated, then it's affecting your latest view of the data also, and it will change the how the analytics will see the data, because it will impact your reporting also. Let's say the report that will looks correct over the day, but when the later updates arrive, that looks no longer be correct. So you have to handle it for both the scenario, for OLAP kind of use cases, even the OLTP kind of use cases also. So with this, let's move on the next slide. As our workload that system we want to build is more of an OLAP kind of workload. We want to build a system that mostly support query like GMV trend, status breakdown, like somebody want to know the count of payment that are stuck in failed state, that are stuck in success state, all those things. But at the same time, there are some use cases on the merchant dashboard that we are more of lookup kind of nature. So those kind of like transactional query, like somebody want to know like what is the payment status currently, what is my current payment status. Somebody want to fetch the last 10 payments for a user, for a merchant. So those use cases also comes in the picture, and then system objective is bit changed from a only OLAP. We want to serve OLAP plus some mixed kind of workload also, where we able to serve these kind of query. And even 70% of our workload is OLAP, but 30% workload we want to serve with more of lookup kind of capability also. So with all these requirements, what we have come up with, this is the high level architecture that very high level that we have come up. So here if you can see that we have POS and online, that is a major payment sources that the transaction got initiated. Then it's land to our transactional DB like Aurora or Dynamo. From there we have a change data captures, and that will flow to the Kafka, and that will get processed by a stream processing engine like Spark. And finally it land to our storage layer, and from there it will serve to the various analytic use cases. So the harder part is to choosing this OLAP layer. So based on our use cases, as we discussed, like we are majorly on OLAP and all. So ClickHouse was the natural choice for us, and we have chosen ClickHouse as our OLAP store. And because if you think about ClickHouse, ClickHouse is a more of a columnar storage, and it is built for OLAP kind of query, and it built for OLAP scale very well, and it works very fast for an OLAP kind of query. So let's deep dive more on the ClickHouse part, like how ClickHouse works, how ClickHouse store the data, what are the internals of ClickHouse. So if you think about ClickHouse, for a table, ClickHouse stores data in multiple parts, and these parts are immutable in nature. So whenever a new sets of row got inserted into the ClickHouse, it will create a data parts, and these parts were immutable in nature. So if you think from a payment perspective, whenever a payment arrived, let's say 10 o'clock payment got created, then within a 5 seconds it got approved, and at 12 seconds it got captured. So if you see from the diagram that this payment, when it's got created and it go to the multiple transition, then in ClickHouse it will create a multiple version of the same payment, and these version can exist in a same data part also, and it can exist in the multiple data parts also. And so that is the storage model of the ClickHouse. It will keep creating the different version, and once these data parts got created, then it will use a replacing merge tree algorithm to merge these data parts and create a latest version of the data with the latest data parts. So these merge is happening in the background. So what are the consequences of this is that this is good design for a high throughput writes, because it's not changing your row again and again. It's creating a new version of that. But the consequence of this, your correctness depends on the background merges. At storage layer, your correctness is not immediate. It will come after background merge will happen. And so that is the overall design of the ClickHouse. So let's move on. Like once we started this in our real system and in production system, how it works, what are the challenges we face. So let's talk about those things. So when you think about this also, so now your query correctness is become, whenever query comes, Its correctness is become how these versions are resolved at the read time. How these versions are get resolved, that's matter for the query correctness. Yeah. So this system works well for us for initially when we have a low volume and when we have put a few months of data. This system behave well and we not face much issues on that. But as we grow our scale and we started data volume is growing, then we started facing multiple issues with the systems. And as we mentioned, some of the issues like we started facing that queries are getting timeout and some of the query latency got increased. Then we also facing issues like some queries are getting stale data. And then we also facing issue of deduplication. So like our query are getting inconsistent result because of the multiple parts of the data for a single payment entity. So let's deep dive more like why these issues are happening, because as we understand more on the ClickHouse storage layer, let's deep dive more like what are the causing these issues to happen. So if you think about when a payment is, as we seen in the last slide, when a payment is going to the multiple transition state, it's got multiple version of the data is created in the storage layer. So physically, there are three versions of or multiple version of the data in storage, but logically this is a single payment entity. So whenever a query reads, it will read not a single row for a payment, it will reading the multiple row for a payment. And that's lead to the two type of issue, like for an OLAP kind of query, when somebody trying to create a find out the GMV or aggregate kind of some query, then the data got inflated because same payment that is used to be count once, it will counting multiple times for the same payment. For OLTP kind of query, you get the older version of the data and that's caused the stale problem. To fix these issues and all, ClickHouse provide a feature called final. So what final does is, so this final keyword that you can put at the query layer, and what final do is, final will give you the your deduplication problem will shift at the query layer. So your query has to do the more work. It has to deduplicate the data, it has to scan all the versions, then it has to do all the deduplication, and then it can give you the correct result. So that is the main trade-off here. Like if you want the correctness, then your query become costly and your latency also increase because query has to do the more work. So now you have to take a trade-off, like if you want correctness, you have to pay more cost and more latency. And if you do not pay the more cost and more, then your data will be not correct. So that is the trade-off that we find out when we put it in production and for a high volume scale. And if you think about this, this is not a problem that ClickHouse is bad at analytics. It is about the problem of getting the correctness with the correctness is getting costlier here. It is that problem. So now our problem become more of how we can make the correctness cheaper, because now the problem is not about the correctness, because correctness we can solve through final, but now the problem become how we can make the correctness to be cheaper, because that is getting costly for us because the deduplication is happening at the query layer. So let's move on the next slide to solve this correctness problem. And as I talk about to how we can reduce the cost for getting the correctness, we tried multiple optimization on the ClickHouse. So first optimization that we tried is called RMS. So ClickHouse provide a capability called RMS where you can pre-aggregate some of the column data, and that will help you in pre-aggregating those columns. But those also come with some challenges. Then we also tried pre-wear conditions, pre-wear optimization. We also try order by, and we also try the background merges, proactively background merges. But all these solutions come with this will give us some boost up in the performance, but still it's not enough where we want to achieve. And this will also come up with some trade-offs like some operational complexity, all those things. So with this thinking, what we have to do is that is the time that we have to think of, like is this the right architecture that we have come up, is based on our workload model. So that is the point we have to push our thinking from this perspective, that It is not about optimization problem. It will become the architectural fit problem for us now. And that is the point we started evaluating other than ClickHouse, what is the solution that is good fit for our architecture. And that is the point we started thinking about H-step kind of architecture. So what is H-step? H-step is hybrid transactional analytical processing model. So how it's different in terms of H-step? H-step, for H-step, what is the thing is, it will keep your transactional truth as well as performance analytics. Both are the first class requirement in a H-step model. And how it do that? In a step model, you have a transactional, your transactional state will be maintained by the transactional side, and that is the latest truth correctness of the data. And that transactional side will sync continuously to the analytical side, and that will take the guarantee of freshness of data at the analytical side also. So let's deep dive more on the H types of databases. So TidyB is one of the database that provide the H-type kind of solution. Where if you heard about TidyB, TidyB is an open source distributed system based on the MySQL protocol. And how TidyB provide both of these, like it provide you the OLTP workload analytics also, as well as OLAP also. So it will provide you both type of system, OLTP and OLAP. And so how TidyB work is, this is the high level architecture of the TidyB, where you can see that there is a TidyB server, and then it is a TiKV nodes, and then it is a TiFlash nodes. So what a TiKV nodes is? TiKV nodes is your row oriented design, where it will store the data in row oriented format, and that is well suited for your OLTP kind of query, and that is where the transactional truth is maintained, where there is a it will give you the ACID guarantees. And then there is a TiFlash kind of nodes, where the same data got synced through the Raft protocol from the TiKV node to TiFlash nodes. And when it syncing the data, it will convert the data into the columnar format. And this will become your analytical source, because all the analytical query will query from here through the columnar format. And that is well suited for your scan, joins, aggregation type of query. And then on top of this, it has a TidyB server. So whenever you submit a query, it will go to the TidyB server, and that will parse your query, make a plan for your query, and then it is an optimizer that will decide based on your plan, like is it well suited for the TiKV node or is it well suited for the TiFlash node. So that's all our purpose, like we are getting the correctness as well as we are getting the analytical workload is sorted by our TiFlash node. Our correctness is also sorted because that is come from the TiKV node, and that will make sure that we getting both the things. And apart from that, it also solving one more problem, that your TiFlash node and your TiKV node are workload isolated. So because both are the different, you can put resource, both are work on different type of resources. So if your OLAP kind of workload is more, then you can put higher resources on TiFlash node, and if your OLTP workload is less, you can put less resources on the TiKV node. So it will give you that feature also, that your workload will be isolated and your OLTP query will not be affecting OLAP kind of query, and vice versa. So let's understand more about how this sync work, like when we say that this Raft sync will work. So I will deep dive more and touch upon this, how the TidyB able to sync this data from TiKV node to TiFlash node in real time. So if you think about, this is the high level architecture internal, like how TidyB store the data. So TidyB store the data in forms of region, and then these region are nothing but so it is a basically key value pair, and it will divide these key value pair into range of keys, and these single range of key will become a region. And because this is a distributed system, so it will replicate each region into the multiple nodes, and these multiple nodes will become a quorum that every distributed system will have, and we call it a Raft group. And then it uses Raft consensus algorithm to sync data from leader to follower. So in a Raft group, you have one leader for every region, and then you have a follower for every region. So it will use raft algorithm to sync data from the leader node to the follower node. And so one more thing is, another point to touch here is, this is the simple model for the TiKV. But now to introduce the TiFlash node, what they have changed is, they have changed in the raft algorithm to introduce a new node called learner node. So what this learner node do is, it will sync the data from the leader node asynchronously. And why this has been done, you can ask the question like, why not add one more follower node as a TiFlash node? Because if we add one more follower node, then it's become a part of quorum. And that will affect the transactional path. Because until the quorum is not complete, your transaction will not complete. And that will slow down the transaction. So so that transaction will not affect it, it will introduce a learner node. And that learner node will sync the data from the leader asynchronously. And while it's syncing the data, it will also convert the data from the row format to columnar format and store in the TiFlash nodes. So that way, this is sync is real time. This is happening in real time with a few very low latency. And that way you get the correctness also, and you will get advantage of OLAP kind of query also. So let's move on the next slide. This is the some of the benchmark that we have done for our data sets. And as you can clearly see, with ClickHouse, we are getting a latency from 4 seconds to 12 seconds. This is based on the different type of queries. With SIF, with the TiDB, we are getting the queries latency from millisecond to few seconds. And that is not only about the latency, it is also about the correctness. With TiDB, we are getting the data as fresh as the transaction is happening. So, and if you see this benchmark, it does not tell you that one system is better always over the other system. It will tell you that your system will depends on your workload. So it will give you that picture that it's not like universally that always TiDB will perform better than ClickHouse. It will match your architecture pattern. Your workload pattern is good, matching your TiDB, and that's why your TiDB perform better for us. So with that, I will come to the key takeaways that with our journey. So this is the majorly some takeaway that our journey taught us. Like whenever you're choosing a system, you will not say that my workload is OLAP and you stop there. You cannot choose a system just based on the label that, okay, my workload is OLAP and I will choose an OLAP system that will work for me. You have to ask some questions around your workload also before choosing a storage layer. So you have to ask questions like, what is my data nature? Is it an append-only data, or is it a highly mutable data? Because that will change everything. Because the system that works for append-only data will behave very differently for the highly mutable entities. You have to ask questions like, how many updates your each row will get. So like if your updates are very minimal, let's say 1 or 2 updates, then in that case, even the deduplication can work. But if your entity is highly mutable and it's changing again and again, then the cost of deduplication becomes very high. Then you have to ask question like, what is your latency requirement? Is you okay with the sub-second latency, or do you need the freshness in the data also? You have to take care of access patterns also, like is your workload is only OLAP, or you want to do some scan aggregations query only, or you want to do some kind of lookup queries also. So it's a mixed workload or it's a OLAP workload, that also you want to understand. And the last question you have to think about is the consistency, like is your workload is good, and is your requirement is that you can wait for the background merges that we have seen in the ClickHouse. Like if you can wait for the background merges, then you can get the correctness. But if you cannot wait for the background merges, and then your cost will become higher if you push the deduplication at the query layer. So this is the last final takeaway that I will want to go away. Like so, for our journey, we have migrated from OLAP kind of system to the HTAP kind of system. For us, the migration is not only about is because of that we want the data correctness also, and that is the where our OLAP system is becoming costly, and that's why we have to take a architectural shift from OLAP kind of system to an HTAP kind of system. And it's not like that OLAP kind of system does not work. It will work for very different set of workloads, and it works well for append kind of workload where data is not mutable. So it also, so whenever you're choosing a system, it depends like what is your workload nature, what is your freshness, what is your query pattern, what is your data mutability pattern. All these you have to take care, and even you have to ask like, is my workload model matching with the data storage pattern of the system I am choosing? Like in the ClickHouse, how the data store work internally, you have to understand that also. So that is the final takeaway I want to give. Like whenever you're choosing a system, think about those all aspects also, and based on that, design your system rather than just choosing based on the label. Yeah, I finish at this point, and if you have any questions, I am ready to help.
Hi, this is Amit.
Yeah.
In your last slide, I saw that the movement that you have done is from OLAP to hybrid to unified step system. So how do you ensure that the end users who are using these platforms, because these three talk a different dialect, different syntax, different mechanisms as well. So how do you ensure that the end users don't see any changes while you are doing the migration or you are moving from one system to another system? How do you ensure that?
Yeah, so for that, what we have done is we do not directly expose any database to end user. We have a middle layer, we call it a WDA, like warm access layer. And every system that want to connect to the database, that will go through the warm layer. And also whenever we do any migration on database or anything, this warm layer will take care of all the SQL dialect changes or any transformation. So end user do not have to affect like at the backend what system you are using. They only will use the WDA layer, and the backend you can always change your system.
Okay, so that's the layer which talks in terms
Yeah.
of abstraction. Okay, thanks.
Are there some benchmarks or numbers available on the concurrency as well? And how does TiDB perform as the scale grows? Is there a provision for segregating hot and cold storage, or it is able to perform well at a bigger hot storage as well?
Yeah, there are some public benchmark also, and we also have done our benchmark. So even for us, we are running a TiDB at 100 to 120 TB of data, and it's performed well. But yeah, at some point of time, every database has some limitation. So at some point of time, your operational overhead become more complex as your volume will grow. And with the latest TiDB version, it also have a hot and cold system where you can archive your older data to S3. It has that fine features also, and that will work well also for that.
Hi Anuj, thanks for the talk. Anuj, I want to understand the TiDB part that you showed. There were two components to it. One was the OLTP part that was working synchronously, and then there was the OLAP part that was working asynchronously. So how is this system different from another system like a Postgres cluster or some similar database which keeps processing your transactions, and then you put on a CDC which asynchronously syncs your data to something like ClickHouse? So why are these two systems different? Because they seem to be out of sync for quite some time, right?
No, so as I mentioned that this is a very low latency sync like any distributed system, like, and this is internally happen through raft sync algorithm that will uh, take care of like your system is always consistent. And it's different from ClickHouse. As I told you, like in ClickHouse, you have to wait for the background merges, and that background merge is happening sometime in 10 minutes, sometimes 50. It's not always like, it depends on like when background merge happen, and that you will get the consistent view. In this case, you always get the consistent view because this sync is more of like a distributed system, like how sync happening between the multiple nodes, and it will always make sure that you always getting the latest version of the data. And in terms of if you talking about like if you build something like CDC and all, so that has another challenges in terms of like you have to build some pipelines, and that will another delay. It's not, you cannot serve through pipelines within a millisecond delay. because the pipeline has to consume the data, it has to run, and then also come with some additional cost also to running those pipelines.
Sure. Thanks, Anuj.
Thank you. Thank you, folks. In favor of time, we'll have to close